Welcome to The Explainer. Today, we are diving deep into the brilliant, sparkling world of gemstones. But, beneath all that beauty, there's a really modern mystery. How can something made in a lab be identical to something that took like billions of years for the Earth to form? And if they really are identical, how in the world can we tell them apart?
Okay, so take a look here. On one side, you've got a sapphire that was pulled from deep within the Earth. On the other, one created in a lab. They look the same, they feel the same, and get this, they have the exact same chemical formula, Al2O3, aluminum oxide. We're talking atom for atom, they are the exact same thing.
So yeah, that leads us right to the big question. If they are chemically the same, how can anyone possibly tell the difference? I mean, it seems impossible, right? But it's not. To figure this out, we're going to have to put on our detective hats.
All right, so like any good investigation, we have to start with the lingo. To solve this mystery, we first need to get a handle on what a lab-grown gem actually is. It's a classic case of being totally real, just not natural.
Let's be super clear about this. A lab-grown gem is not fake. It's not a simulant like, cubic zirconia or glass. It has the exact same chemical makeup, the same hardness, the same way it plays with light as a stone dug out of the ground. The only thing that's different is its origin story.
So because they're real, but have that different origin, you've got regulatory bodies like the U.S. Federal Trade Commission, the FTC, enforcing some pretty strict labeling. Sellers have to be transparent, using the terms you see here, laboratory-grown or even synthetic. Now, this isn't really about value. It's all about honesty, about giving the buyer the complete story.
Okay, so if they aren't being mined, how exactly are they forged inside a lab? Let's take a peek behind the curtain. How do scientists pull off something that takes Mother Nature millions and millions of years to do?
Well, it really just boils down to two main ways of doing it. You can think of the first one, direct melt, as kind of the brute force method. It's like flash freezing a liquid into a perfect crystal. The second one, solution growth, is a bit more patient. It's like gently coaxing a crystal to grow out of a rich chemical soup.
So these direct melt methods, they all basically follow the same script. You take the raw ingredients of the gem, let's say aluminum oxide for a ruby, you melt them down at insane temperatures, and then you cool that liquid in a very, very controlled way. Whether you call it flame fusion or the Czochralski method, the goal is the same. You're trying to convince that liquid to solidify into one big, perfect crystal.
Now, solution growth? Yeah, that's a lot more like gardening. Scientists dissolve all the chemical ingredients into a liquid, either a special solvent they call a flux or just superheated water. Then, they drop in a tiny little seed crystal of the gem they want to make, and over weeks, sometimes even months, new atoms come along and lock into place, and the gem just grows and grows around that seed.
And the technology for this stuff is incredibly specialized. I mean, for a gem that's famously tough, like a diamond, you need some extreme methods. Think high pressure, high temperature, or HPHT, which basically mimics the crushing conditions deep inside the Earth. Or chemical vapor deposition, CVD, which is almost like 3D printing a diamond, atom by atom. The point is, this is some seriously sophisticated science.
But after all that incredible science, we are right back where we started. Whether we're talking about a ruby, a spinel, or a beryl, the lab-grown version has the exact same chemical formula as the one from the ground. The journey was totally different, but they arrived at the same destination. So, how do we solve this?
This is where the real fun begins. This is where the detective work really kicks in. Since the main formula is identical, we have to look for clues that are hidden on a microscopic level. We are on the hunt for a unique chemical fingerprint. You see, the secret isn't in the main ingredients. It's in the trace elements. We have to stop looking at the millions of aluminum and oxygen atoms in a ruby and instead focus on the handful of accidental atoms that just snuck in while it was being born.
Which, of course, begs the question, why would the trace elements be any different? Well, just take a second and picture the two birthplaces. One is the chaotic, messy, unpredictable environment deep inside the Earth. The other is a sterile, perfectly controlled, high-tech laboratory.
The difference is all about the neighborhood. A mined gem grows up surrounded by all kinds of rock and groundwater, and it soaks up tiny geological impurities along the way. But a lab-grown gem,
It grows inside a man-made machine. So its impurities come from the equipment itself, from the metal crucible holding the molten goo, from the furnace walls, from the chemicals used in the whole process.
And these lab contaminants, well, they're the smoking gun. Using really advanced equipment, gemologists can actually find microscopic traces of metals like platinum or gold or iridium inside a gem. These elements could only have come from the crucible it grew in, and finding them is a dead giveaway of a lab origin. It's like a tiny made-in-a-lab tag.
So how do we bring all these clues together? We're finally ready to crack the code and lay out the telltale signs that absolutely separate a lab gem from a mined one.
The whole identification process is basically a two-part test. First, you look for the telltale presence. That means finding those lab-specific elements, like platinum, that just shouldn't be there. But just as important is the telltale absence. Sometimes a lab gem gives itself away because it's too perfect. It's missing that messy, random fingerprint of geological stuff you'd find in a natural stone.
Here is a perfect example. Natural emeralds almost always form where there's water, so they trap these microscopic droplets inside them as they grow. But a flux-grown emerald is made in a totally water-free process. So if a gemologist peers inside an emerald and finds no water, that absence is a crystal-clear fingerprint of a lab origin.
And we see the exact same thing with rubies and sapphires. The raw materials they use in the lab are incredibly pure, so the final gems often have way lower levels of elements like these, magnesium, iron, gallium, which are pretty common hitchhikers in mined gems. In a weird way, their very purity is what gives them away.
So the solution to our whole mystery is this. You don't identify a lab gem by what it is. You identify it by what it contains. You look for the tiny telltale traces of its man-made birthplace, or for the geological traces that are conspicuously missing. It is all about finding that subtle but absolutely definitive chemical fingerprint.
So now you know the secret. You can solve the puzzle.
But this leaves us with one last question, and it's a little more philosophical. Does knowing where a gem came from, billions of years in the earth versus a few weeks in a lab, does that change its beauty in your eyes? That's a question science can't answer. Thanks for joining us on The Explainer.